My name is Ryan Tolbin. I'm here with Ashwin Venkataraman, and we're going over 2DFQ, two-dimensional fair queuing for multi-tenant cloud services. And you can see the original authors of the paper there at the bottom. So the motivation for this paper is the unique situation that sharing resources in the cloud encounters. So you will often have multiple tenants that are actually functioning within the same process, which has a thread pool to use all sorts of different resources. So the variability of resources is kind of important in that you may be dealing with a configuration manager, you may be dealing with a database, you don't really know what it's going to be. So your requests may take a long time, they may take a short time, they may be very time dependent, you need to get it back quickly. It may not matter how quickly you get it back. Those things make it kind of difficult to schedule. The real thing that makes it difficult is the fact that you're typically functioning within the same process. So these tenants may all be in the same process, competing to get access to these resources. And the thing they get access through is the scheduler. So they submit requests to the scheduler, and then the scheduler utilizes its worker threads on the thread pool to make sure those resources get to the people who need them fairly. So we're dealing with fair queuing algorithms here. The important thing is that if tenant 1, tenant 2, and tenant 3 are all paying for this service, they all should be receiving the service. And we're actually going to talk about weighted fair queuing algorithms, so you can adjust it for the different tenants in accordance with what they pay, or I guess what their needs are as well. So one of the things that's been learned from actually having this infrastructure in the real world is that tenants can't be trusted. So tenants are basically competing within the same process for resources. And typically in the past, when this has happened, you are dealing with packets coming from interfaces competing to get routed to where they're going, or you are dealing with processes competing with a scheduler to have runtime or things like that, things that usually happen at the operating system level. And that's not the case here. Here they are inside a process trying to get at those resources. So the long and the short of it is aggressive tenants can deny service to well-behaved tenants. So you may have somebody playing by the rules. If you have somebody who is not, either deliberately or unintentionally, it's going to be very difficult for the well-behaved tenants to actually get a fair share of the resources. And one of the things they cited in this paper was this quote by Chris Lee, written in a blog post called Quality of Service in Hadoop, and it says, any poorly written MapReduce job is a potential distributed denial of service attack. And if you think about MapReduce as a way of solving problems, right? You are basically taking something and doing it in a highly parallel fashion for the purpose of utilizing resources as quickly as possible. So you have a problem that may be difficult without large-scale parallelization. When you do that, when you actually do break something up, you're going to use these resources as quickly as possible. And if your tenants are doing that, or if your tenants are coming from that, that distributed idea of solving problems, you can expect that some tenants are going to be unfairly monopolizing resources over other tenants. So some of the initial approaches to this problem, some of they refer to in the paper as coarse-grained approaches, are like the token bucket algorithms. So basically you have an incoming request, and that request requires a token to get processed and used, and that token comes from what's typically referred to as a bucket, or sometimes a leaky bucket. And it can pull one token out of the bucket and then make the outgoing request. The tokens enter the bucket at a constant rate, but having a bucket allows for bursts of request activity. So like right now in this diagram, we have 6 tokens inside the bucket. So in theory, we could have 6 requests come in one after another, and they would all be handled due to the burst capacity of that bucket. But from that point on, it would only happen at a constant rate as the tokens enter the bucket. So this approach was designed to like I said, prevent resource monopolization, to basically make sure that the requests were handled well. It turns out it's not as fair as it could be. And in these services where you have people paying for a certain level of service, it's very important that you be able to show them that you are providing those services fairly. So the token bucket approach does work for coarse grain situations, but as far as having that fine grain control and being able to weight your resource users accordingly and make sure people get the share you want to set them up for, this does not do it. So here's our scheduling scenario that we're going to examine, and this is once again unique to the cloud architecture that we're talking about. We've got 3 different people making requests. We have A, B, C, and D. And these different APIs may be asking for different things. Like if you look at A has it takes 1 time unit for A to complete what it wants to do. Excuse me. 1 time unit for it to complete what it wants to do, as does B. So it has a start time of 0, a finish time of 1, start time of 1, a finish time of 2. B is the same way. So this may be, a short, quick response, part of a user interface, calling a REST API somewhere, where it's meant to just get that back quickly and get that up on the screen. Meanwhile, over here, C and D have things that take longer periods of time. It's actually working in chunks of 4. So C needs to run for 4 time units. D needs to run for 4 time units as well. In a perfect scenario, we would take A and B, put them on worker thread 1, and have them go back and forth. That way we can provide the responsivity that we need for A and the responsivity that we need for B that they're expecting. And for C and D, we could put them on worker thread 0 and have them basically go back and forth. And if we do that, you will end up with C and D fairly using the resources and getting what they want, and you'll have A and B doing the same kind of thing. And you'll be able to have that information come back from A and B quickly, and you'll avoid the bursty schedules that we're going to see in a second. So our current methods of fair queuing both come from the networking end of things, and they're both packet schedulers. That's weighted fair queuing and worst case weighted fair queuing. So weighted fair queuing is exactly what you would think of when you think of a fair queuing algorithm. You keep track of how much of a resource somebody has used. You make sure they don't go past their limit. Time increases in units of capacity divided by threads. So each request is going to come in, specify how long it's going to take, and you're going to use that to make sure that nobody is getting more than their fair share. And you're going to schedule things so that that occurs. The problem is you end up with a bursty schedule when you do this. So when I say a bursty schedule, I mean A is running in time unit 0, 1, 3, 0, 1, 2, and 3, right? One after another. And then it has this pause of 4 time units. Then it has another burst and a pause and another burst because it's running back and forth with C. And C needs 4 time units contiguously in order to complete what it's doing. So this is going to provide a poor quality of service for the API that's running as A. Likewise, our other worker thread is doing the same kind of thing under WFQ. It's pretty much mirroring W0 exactly, right? But it's doing it with B and D. So worst case fair weighted fair queuing, WF squared Q, was an attempt to solve actually a very specific burstiness problem that was almost unique to packet scheduling. And that problem stems from the fact that things can come in with their, only requesting a small amount of resource cost, and they will get service right away. And that prevents some of the things that have larger resource costs from running. So what you do is you have this ideal algorithm, generalized processor sharing, and you see if something would run under GPS. And if you would run under GPS, if it's your time, then you are made eligible and you can run. If it's not your time, they're not allowed to run. And this prevents that bursty problem in packet scheduling where the small packets can kind of dominate the scenario. But for us, where we're dealing with something much more complicated, it still creates a bursty schedule for our particular scenario. So if you look at what we set up before, if you look at it running, you will see A1 running and then C1 running for 4 time units. And then A does that burst again, A2, A3, A4, A5, and then C2. And the burst is almost equivalent to what we're experiencing over here in weighted fair queuing. So WF squared Q really isn't a solution to our problem in this particular case. So when they were designing 2DFQ, well, if you want to understand the design of 2DFQ, you can think of it in terms of children lining up in a preschool class to get stickers from a teacher. And the children know how many stickers they're going to ask for. The important thing for the teacher is that at the end of the day, all the children get the same amount of stickers. So it is a fair queuing scenario. And if you implemented that with WFQ, you basically keep track of how many stickers each child has, and you move back and forth between them just to make sure nobody exceeds that limit. If you add some of the peculiarities or some of the special things about WF squared Q, you're also going to throw in that idea of GPS time, where a student who may keep coming up asking for one sticker, eventually is going to get told they have to wait until their time to ask for a sticker. And neither teacher will hand out stickers until a student reaches that particular time. Once again, not an ideal solution. In 2DFQ, you can actually split your teachers up according to who you want to be a fast teacher and who you want to be a slow teacher. So your fast teacher may handle your requests for 1 sticker, 2 stickers. Slow teacher is going to handle your requests for significantly more stickers, say 4 stickers or 6 stickers. By breaking up your worker threads into those different units, you can make sure that your students get the best service possible. And that's the same thing that 2DFQ is doing with its resource requests. So here's how it looks. This is a thread occupancy chart, and it's showing you basically how the different threads are utilized and which ones end up filled up with very small requests and which ones end up filled up with large requests. And in order to make it spaced out like this, right, you need to change the way that requests become eligible inside these different threads. So what 2DFQ really is, it's a modification to WF squared Q that changes the eligibility criterion to make it so that things move around to different threads. And if you don't move things to different threads, depending on their resource cost, you end up with a scenario like we see here in WF squared Q, where it's oscillating. See these gaps in between? So it's oscillating back and forth and back and forth. And over here in WFQ, we don't have that oscillation at all, but also we don't have this properly organized to provide us the best quality of service. 2DFQ will put things in different worker threads depending on the resource cost and depending on the number of worker thread that is. And that's what really makes all the difference. So here's how it does it. This is the modification to the time at which a request is eligible to be run. So you start with your virtual time that you would normally experience in WF squared Q, but then you're subtracting, right, the index of the thread that you are looking at divided by the number of threads there are times the resource usage estimate. So as you get towards the high threads, you're approaching 1 right here, you could have an adjustment by your whole resource usage estimate at the top end of this. And then you have an adjustment of fractions of it corresponding to how many threads are in the system all the way on down. And what this allows it to do is those short bursty requests run on the lower levels, and those longer ones end up running up higher. And you can see that reflected if we take our eligibility times and show them actually drawn out according to 2DFQ. So here is your eligibility time for A1 on worker thread 0 is 0. On worker thread 1 is negative 0.5. All right, and you'll notice that the lower numbers here mean it's going to be eligible to run faster, so that is the thread that it's going to prefer. And worker thread 1 ends up being the preferred thread over time for API A. Meanwhile, API B is doing the exact same thing because it has the same numbers. It's also going to end up preferring worker thread 1. API C, running in these units, these blocks of 4, is going to end up preferring worker thread 0 over time, and the same thing's going to happen with D. And so if you look at the schedule that's created out of all this, you will see, with the exception of this initial condition right here, eventually it trends towards that perfect schedule that we brought up earlier. So this is going to provide a better quality of service for your clients that are using API A and API B than it is for for under WFQ or WF squared Q. So it really does a nice job of trying to get at that ideal scheduling. So one of the interesting things is this is a chart, the thread utilization chart from actual data from Microsoft Azure. And you can see that even with real data, it's doing exactly what we thought. We have the lower threads on the bottom here starting at 0. This is a situation where you got 32 threads. So starting at 0, working all the way up to 31, you can see how the threads are actually varying in how they're being utilized with real data from Microsoft. And you can also see in WF squared Q, that oscillation is not quite as pronounced with real data as it is in our simulation. And WFQ really still, it's fair, but it's scattered all over the place. So then the question becomes, what do you do if the resource costs are not known? So up until now, even in our analogy, we had the school kids coming up and telling us exactly how many stickers they wanted. Well, what if you have a resource request that has an unknown resource cost? And what they added in the paper is 2DFQE. And 2DFQE accounts for that situation.
Hey, this is Ashwin. So let me start off with the theorem they use for 2DFQ. So this is a theorem which is explaining the fact about proving how far the tenants can fall behind the fair share provided by the ideal fluid GPS server. And here are the values WF2DFQ 0, T, which represents the number of resources consumed by the tenant. F under 2DFQ, and WF GPS 0, 2T actually represents the resources consumed by F under GPS. So GPS here is general processor sharing, and the number of threads and is N, and the L max is the maximum resource consumed by any request in the system. So moving on to the next slide, we are explaining about 2DFQE, which is the pessimistic estimation. And there are two types, retroactive charging and refresh charging. And since the costs aren't actually known, and most schedulers update counters at schedule time using an estimate of the cost, example by using a moving average that is updated when the requests are complete. So here the retroactive charging ensures that a tenant is eventually charged for the resources it actually consumes, and it's not just a priori estimate. And it is important to have a good cost estimator to avoid bursty schedules in short term. So and the retroactive charging will refund the unused cost to the tenant, thereby guaranteeing that it will receive its fair share and in the long run, which is obtained. And most importantly, the overestimation does not cause the prolonged thread pool blocking for other tenants. And talking more about the refresh charging. So refresh charging is a damage control mechanism that is periodically measured, and the resources usage of long running requests, and incorporates the measurements into the scheduler immediately. It lets us notice expensive requests quickly and immediately, and charge the tenant for the excess cost while the request is still running. And the short circuiting of the typical cost estimation is a feedback loop. So the computational overhead is measured, and the resource consumption is actually non-negligible. So you have a huge overhead cost, and there must be a balance between the frequent measurement and the acceptable overheads. So this is about the pessimistic estimation in 2DFQE. And moving on to the algorithm. So there are actually n threads in 2DFQE algorithm, and A is the set of active tenants. So CJF keeps track of how much credit we have left for this request. So, and it is initialized in line 23, if we see here. And so this is how much you paid for RJF. So that is about it. And if we still have credit, we subtract it from line number 12 here. And otherwise, we increase the tenant's clock forward, and which is here in line 14 after the else, if after the if else statement. And we reconcile the final resource measurement with remaining credit in line 31. So which is here, reconcile is being used. And we update the per tenant LF max estimate on line number 30 here, which is here. So we update the per tenant LF max here, and we use it for the eligibility and finish time calculation in line number 20 and line number 24. So here in line number 20 and 24, we use the LF max. And moving on to the next slide. So you're able to see three graphs explaining the synthetic workload and the tenants of different fair queuing systems. And the first graph actually explains the service received by a small tenant over time, and it's measured in 100 millisecond intervals. And the bottom graph here explains about the service lags in seconds, which is compared to an ideal GPS server. Over here in the second graph, we are able to see shaded and non-shaded parts. The so it explains about the thread occupancy over time, and the horizontal line represents worker threads, and the shaded part actually indicates the worker is being processed and it has an expensive request, and the unshaded part explains if that it's a cheap request. And in the third graph, we have the standard deviation, and it's expressed in seconds. So the small tenant service lag is in presence, and it's increasingly in many expensive tenants. So we have to note here that the tenant's small request execution time is in 0.001 seconds. So this is about the three graphs. And moving on to the next, we have the evaluation of 2DFQ, and it's about the implementation of all schedulers in discrete event simulator, where the requests were scheduled across fixed number of requests. So and the synthetic workloads and traces from Azure storage to keep the server busy. So this is how they have actually employed the experiments, and so they are comparing the three different types of baseline algorithms, which is 2DFQ and WFQ and WF square Q. And the upcoming thing is the metrics which they use to evaluate the schedulers, and there are different types of metrics they use. It's service lag variation, service rate, latency, and Gini index. So moving to the service lag, the first one, it's the difference between the service of a tenant, which has to be received under GPS, and the actual work done, and the n threads with r rate of processing. So the reference in GPS system is given by the rate of nr, and the service lag variation has is the standard deviation of the service lag, and the bursty schedules have high service lag variation due to the oscillation in service. And the service rate, when the work done is measured, it's actually when the work is done, it's actually measured in 100 milliseconds intervals. And we have the latency, which is the time difference between the request being enqueued and finishing processing. And we actually focus on the 99th percentile of the latency, unless otherwise it's noted. So that's how the authors have found the latency to be around 99th percentile. And the Gini index is the instantaneous measurement of the scheduler fairness, and it's across all the tenants. So that's about it. And the next slide is about the evaluation of the different 2DFQ, and it's kind of like a summary. And so here, when the costs are known for both synthetic and real world workloads, 2DFQ actually provides service to small and medium tenants, that is that has one or two orders of magnitude. When tenants have expensive requests, they maintain, which is the 2DFQ maintains low service lag variation for small tenants. And when the request costs are unknown, the 2DFQE requests the service lag variation by 1 to 2 orders of magnitude for small and medium tenants. And for increasingly unpredictable workloads, so 2DFQE actually improves the tail latency of the predictable tenants by up to actually 100 times. And across a suite of experiments based on the production workloads, 2DFQE improves 99 percentile latency for predictable tenants up to 198 times. So that's a huge amount. And moving on to the next slide, we have the known request costs and the unknown request costs. And they have the authors have actually made a few experiments with it, and we'll be able to find the graph in the next slide. But about the known request costs, the expensive request and production workloads are the two different methods they've used. And for unknown request costs, they have used um, unpredictable workloads and production workloads. So the experiments actually focus on the scheduling with the unknown request costs that may vary by several orders of magnitude. And the authors first evaluated 2DFQ under the workloads with increasingly many expensive requests, and compare with the service provided under WFQ and WF square Q. So the second one is the authors have also evaluated the overall service and the fairness provided by 2DFQ on the workload derived from the production traces. So in expensive requests, they have it seems that they have simulated service received by 100 1,000 backlog tenants sharing servers by 16 worker threads, and each of the capacity is by 1,000 units per second, and it seems that it's varying. It has varying values of n, and they have designated 100 n of the tenants to be expensive and n tenants to be small. And moving on to the production workloads, their experiment was evaluated fair share provided by 2DFQ with workload derived from production traces of Azure storage. And then they simulated the service received by tenants sharing a server of 32 worker threads, each with the capacity of 1 million units. And for unknown requests, the experiments evaluated with the schedulers with request costs of not known priority basis. For unpredictable workloads, they evaluated 2DFQE's pessimistic cost evaluation strategy, and demonstrating how it could co-locate unpredictable expensive tenants, keeping them away from predictable tenants with small requests. And for production workloads, the authors ran a suite of 150 experiments, and then they derived production workloads from the Azure storage, and they simulated the service received by the tenants under WFQE and WF square QE and 2DFQE with randomly varying parameters. So that's about the different experiments. And this is the unpredictable workloads graph and the production workloads graph, which can be seen here. And moving on to the next slide, we have the 2DFQ explaining the differences between the 2DFQ and WF square Q and WFQ. So in this figure, we are able to see that the predictable workloads with low variation at request cost or workloads are preemptible, and the scenario is representative and of the packet scheduling. And the WFQ and WF square Q 2DFQ provide good quality of service, and yeah, because even if the blocking would occur, so at one extreme, the workloads are heavily varying of request costs and completely unpredictable tenants. So in this scenario, all the schedulers would have behaved poorly, which is why we are able to see a drastic reduction. And but 2DFQ does not deteriorate as rapidly as WFQ and WF square Q do. So they don't deteriorate as rapidly as they do, and that's and they have used pessimistic estimation strategy to take advantage of the 2DFQ's cost-based partitioning. And but WFQ and WF square Q lack this cost-based partitioning here, and this is about the overall information regarding WFQ and WF square Q and 2DFQ in different scenarios. And now moving on to the limitations we have in 2DFQ. So while 2DFQ actually tries to improve the quality of service when the system is backlogged, and work conserving schedulers in general cannot actually improve the service when the system is underutilized. So all the worker threads could be servicing expensive requests, uh, and it could, if no other requests are present, any subsequent burst in the small request would have to wait for the expensive requests to finish. So this actually creates a large delay for the small requests. So there are ways to avoid this. So the ways to avoid it is to make the scheduler not work conservingly by allowing threads to remain idle despite the presence of queued requests. Another option is to allow a variable number of worker threads and to spawn new threads when small requests show up. This would oversaturate the CPU, and thus it slows down the already running request though. But it would allow small requests to finish faster. But this would incur additional overhead costs from the context switching. Okay, moving on to the conclusion. Um, the challenges of the queuing in multi-tenant services were actually large in cost variance, and it executes concurrently across many threads. The 2DFQ is but much better than WFQ and WF square Q, which achieves significantly more schedules and can improve the latencies. So 2DFQ is much better in that, and it can actually compete with the large requests as well, which is why 2DFQ is more preferred, and the authors prefer that more than WFQ and WF square Q. So this is about it. Thank you.